Delaware Tech, Chem 100, Chem 110, Unit 2 continued, heat, energy, and temperature. Heat is one of the many forms of energy, and like all forms of energy, is measured in units of joules, or in the imperial system, calories. These are what we call the small c calories. There's another type of calories called the big C calories. These are the capital CAL, and these are the calories you might be familiar with if you're looking at the energy of food on packages in the United States. The unit of 1 calorie, this is the small c calorie, is equal to 4.184 joules exactly, and this is the defined amount. So this was set as being exactly equal to one another. So joules is the metric unit, calories is from the imperial system. Now, 1,000 joules, or a kilojoule, is also related to the calories as shown here. So 1 kilocalorie, this is the small c calorie, is of course 1,000 calories. So we've already learned that the kilo prefix means 1,000, and 1,000 little c calories is actually equal to 1 big C calorie. This is the calorie that you read on the packages of food. So 1 big C calorie is actually equal to 4.184 thousand joules, or 4.184 kilojoules. So please be careful when you're using big C calorie versus little c calorie, but you'll notice in either case that 1 kilocalorie, the normal kilocalorie, is equal to 4.184 kilojoules. And what this means is that a joule is about a quarter of the size of a calorie, and a kilojoule is about a quarter of the size of a kilocalorie, but a kilojoule is about a quarter of the size of a big C calorie. So be careful when you're using these units. If you're in any other country in the world besides the United States, they tend to label their foods in kilojoules, not big C calories. So what that means is if you look at packages, say if you're somewhere in Europe and you buy a candy bar, multiply that number of kilojoules by a number a little bit bigger than 4 to find out how many big C calories you're really consuming. So remember, a little C calorie is about 4 times bigger than a joule, and the nutritional big C calorie is actually 1,000 little C calories, or 1 true kilocalorie. So here's a scale showing you the relative energy values of different amounts of joules, so you get a feeling for joules. If you look at the top here, 10 to the 26 joules, that's 1 followed by 26 zeros. It's that many joules is how much energy the sun produces every second. Now, if you go down a little further, you see that the solar energy reaching the Earth per second is 10 to the 17. What that means is that number is 1/1,000,000,000th of all the energy the sun produces. So the Earth only receives 1 out of 1,000,000,000 of all the energy the sun is producing at any time. One single person only needs 10 to the 11 joules for an entire year of life. So just by comparison, a gallon of gas is about 100 million joules, or 10 to the 8, and eating a single serving of pasta or a donut, or the energy needed to bicycle for an hour, is about 1,000,000, 10 to the 6 joules. So how do we measure the energy in food? Well, we use a device called a calorimeter, and calorimeters are useful not just for food, as you'll see later, but they are useful for determining the energy stored in food. And the fact is, you can't measure heat that's stored in food, or the energy stored in food, directly. You can't measure the heat of anything directly. You have to measure heat as it's being transferred from one object to another. Heat can only be measured as a transferred material. And the easiest way to do that with food is to set it on fire. So we have this device, and this is a very simplified version of a calorimeter. This is one you could actually make even at home if you had a good thermometer. And what you need is a can that has some air holes on the sides, and a little piece of food like a corn chip, which would be sitting on some kind of cork stand to hold it up. and you want to hold it up underneath a container of water, and the container of water has to be fairly close with a good thermometer sitting in it. And the idea here is that while you can't measure the heat stored in the food, the energy stored in the food, the calories stored in the food, you can measure how much heat the food transfers to the water by knowing exactly how much water you have in grams and knowing some properties about water, like what we call the specific heat. Specific heat tells us how hard it is to warm up water if we add heat to water. Remember, heat and temperature are not the same thing. Heat is energy we're adding to the water, and temperature is how much it responds to that energy. So the change in temperature is. So you would take this container, set the corn chip on fire, make sure it's close so you don't lose too much heat going elsewhere to the air around it or to the cans. And the heat will be transferred as it's burning. You literally set the food on fire and let the heat transfer from the corn chip to the water, and then you measure how much heat the water has absorbed. Well, it turns out the amount of heat released from the food, theoretically, if you could do this perfectly, is going to be exactly equal to the amount of heat the water absorbs. Another way to say that is the heat of the food is equal to negative value of the heat to the water, because the water is gaining the heat, the food is losing the heat. That's why the opposite sign. So here's a list of calories, big C calories, which you already know are the same as little c kilocalories. So when you see kilocalories here, K-C-A-L, that's the same as the big C calories you're used to looking at on packages. And you can see, depending on the amount of carbohydrates and fats and proteins, you'll get different totals, and you can always check these for yourself. But we have ways of calculating this. If you don't have a calorimeter to actually run it, you can do a quick and dirty calculation of how much energy your food has if you know these three facts. Carbohydrates have 4 big C calories, or 4 kilocalories per gram of carbohydrate. Proteins have almost exactly the same amount, 4 big C calories, or 4 kilocalories per gram of protein. Fats, however, have more than twice as many calories per gram of fat, about 9 big C calories per gram of fat. So if you remember 4, 4, and 9, 9 is the fat, and the other 2 are 4 big C calories, or kilocalories, for each gram. You can do a quick calculation. Now, this is not the proper way to determine how much energy food has. You really have to use a calorimeter, but this is a quick way to determine, by looking at a package, how much of your calories came from fat or carbohydrates or protein, or what the total calories would be in your food. So here's a quick example. You have a piece of cake. It has 25 grams of carb, 5 grams of fat, 5 grams of protein. Now, when you get these problems, be careful, because they're not always in the same order as the original: carbs, protein, fat. You'll notice here it's carbs, fat, protein. So make sure you multiply by the right numbers. Carbs and protein are 4. Fats are 9 big C calories, or kilocalories, per gram. So we set up our equation where we multiply each number by its appropriate corresponding number, its corresponding conversion factor. So 25 grams of carbs times 4 kilocalories, or big C calories, per gram of carbs. 5 grams of protein times 4 kilocalories per gram of protein, and 5 grams of fat times 9 kilocalories, or big C calories, per gram of fat. And when you multiply these out, you see that you get 100 calories, or big C calories, or kilocalories, from carbs. You get 20 kilocalories, or big C calories, from protein, and you get 45 big C calories, or kilocalories, from fat. And when you add these three numbers together, you get 165 kilocalories, or 165 big C calories. Keeping in mind the average sized woman should get about 2,000 calories, big C calories, a day. The average sized male in the United States should get about 2,500 big C calories per day. So here are the same 3 conversion factors that I already mentioned. Here are 3 new problems. You have a new piece of candy. So this is exactly like the old problem, and you can pause it here and see if you get the right answer. I'll stop for a second. And you basically do this problem exactly the same way we did before, making sure you line up the fat with 9 and the carbs and the proteins with 4 or 4. So we see it's 15 grams of carbs times 4 kilocalories per gram of carbs, 1 gram of protein times 4 kilocalories per gram of protein, and 12 grams of fat times 9 kilocalories per gram of fat. And you see you have 60 kilocalories from carbs, you have 4 kilocalories from protein, and 12 times 9 would be 108 kilocalories from fat. You add these up, and you get 172 kilocalories, or 172 big C calories of energy from this piece of candy. That's a big piece of candy. So look at this next problem. How many grams of fat are in steak that has 4.2 grams of carbs? So a moderate amount of carbs, not an enormous amount. 10.1 grams of protein, good source of protein, and a total number of kilocalories of 82.4 kilocalories, or big C calories. So we don't know how many grams of fat there are. And in the past, I've always told you, okay, solve for your X first before you put numbers. But in this case, it's a lot easier to just write the exact same formula, plug in all the numbers you know. You don't know how many grams of fat. So you end up with this equation. 4.2 grams of carbs times 4, and I won't say the units each time, 10.1 grams of protein times 4, and your unknown grams of fat times 9, and these add up to 82.4 kilocalories. Well, now you solve for the X. So you work out each of the two components, and you'll notice that you get 16.8 kcals, we say kcals or kilocalories, kcals from carbs, 40.4 kcals from protein, and an unknown amount from fat, and the total is 82.4. So you take the 16.8 and the 40.4, subtract it from the 82.4, and then divide by the 9 kilocalories per gram of fat, and you'll get how many grams of fat you have, and in this case, it's 2.8 grams. The last problem has a question where we're dealing with peanut butter, and we give you everything but how many grams of protein. So it says how many grams of protein are in a tablespoon of peanut butter with 8.0 grams of fat, 12.7 grams of carbs, and a total of 154.1 kilocalories, or big C calories. So you set it up exactly the same way as you do in the second problem with your unknown number of grams of protein. So being careful to line up the right food stuff with the right conversion factor. Remember, protein is with 4, carbs are with 4, fat is with 9. And now you solve for the unknown grams of protein. You have 50.8 kcals from carbs. You have 72 kilocalories from fat. You subtract those from the total, and then divide by 4 kilocalories per gram of protein. And you end up determining that there are 7.8 grams of protein. And I will tell you, having worked for a year in a peanut butter factory, peanut butter is actually 51% by weight fat. So peanut butter has a lot of fat, but it also has a lot of protein in it, and it has good carbs. So it's actually quite healthy, even though it has an enormous amount of fat in it. And they're fairly healthy fats from what I understand. Let's talk about heat as it relates to temperature. Heat, as I mentioned, is the total internal energy. I didn't say it in these words, but heat is the total internal energy or molecular motion of a substance. And we really can't measure this directly. We can only measure it when it's transferred from one object to another. For instance, when we burn food, it will transfer its heat energy to the water in the calorimeter. You can also have a piece of hot metal that you drop in water, and it will transfer its heat to the water. So heat can be measured when it's transferred, and we use Q or H to represent heat depending on how we're using heat in what particular context in chemistry. Thermal energy is the kinetic energy associated with random motion of molecules. So every substance has molecules or atoms in it that are moving. Even if they don't look like they're moving, they might be vibrating. And the faster they're moving, the more kinetic energy they have, because remember, kinetic energy is based on movement. So they move faster, they have higher kinetic energy. Higher kinetic energy means means that there's actually a higher temperature. So this energy is the thermal energy in an object. So thermal energy is kinetic energy that's the result of motion of the atoms and molecules in a substance. And the more kinetic energy you have, the higher the temperature. So temperature is really just a measure of this kinetic energy, or another way to say that is it's a measure of the average speed of the molecules or atoms in motion in that substance. And you'll notice I've mentioned that some of these are extensive and some of these are intensive. Extensive properties means they depend on how much matter you have. And intensive means they're internal properties. In other words, it doesn't matter whether I measure a small amount of material or a large amount of material, I'll get the same property. In other words, if I have a piece of metal that's 30 degrees centigrade, and if I take just a small part of that metal, it's still 30 degrees centigrade, or if I took a large part of the metal, it's 30 degrees centigrade. However, heat and thermal energy, these are forms of energy, they will depend on how much material I have. If I have a small piece of metal that's 30 degrees centigrade, well, that has a small amount of energy, heat and thermal energy, or thermal energy. And if I have a large piece of metal, there's a more total energy in there. So that's what intensive and extensive means. So, for example, if I had a beaker here, I have two beakers. One has about, it looks like half, well, let's say half of the other. So the left beaker has half the water of the right, and they both have the same temperature. And in this case, the temperature is very high. It's right at boiling, so I'm surprised they don't show them boiling here. 100 degrees centigrade, that's actually the boiling temperature of water. 0 degrees centigrade is the freezing point of water. So you might have learned these in your studies in Fahrenheit. So I'm just going to write this real quickly here. So the freezing point, and let me get the pen to work, the freezing point of water, which is the same thing as the melting point of water, is 0 degrees centigrade. And this is very easy to remember. In Fahrenheit, you might know that it's 32 degrees Fahrenheit. Whereas the boiling point of water, of course the opposite would be the condensing point of water, but we never use that term. The boiling point of water is set at 100 degrees centigrade, and this corresponds to 212 degrees Fahrenheit. Now, why do I bring this up? Well, you see, the centigrade numbers, 100 for boiling and 0 for freezing, very easy to remember, 0 to 100. And this means that there's a difference in temperature of 100 degrees in the centigrade scale. Well, the person, let's talk about the word centigrade. Centigrade, centi, remember, centi is from a word that means 100. You remembered that centi means 100th, so the scale was broken up into 100 parts. So what happened was there was a scientist years ago who took a glass tube that had mercury in it. So mercury is a liquid. It's a liquid metal. It's very easy to see. It's silver colored. And when he put it in ice water, he found that the mercury contracted, and he marked the point on his glass tube, and he called that 1 number. And then he raised the temperature by taking the same tube, which we'll now call a thermometer, and he put it in boiling water. So this one's in freezing water. It's ice and water. And this one's in boiling water. And he found that the mercury expanded and moved up very high on the thermometer, and he marked that. And he then took that thermometer with these 2 points marked on it, one here and one here, and he divided it up into 100 steps. Well, 100, each step was 100th of the original, centi, and the root word for step is grade, and that's where we get the word grade, as in grades in school. They are individual steps going from first grade to second grade. It's the same thing with the centigrade scale. It literally means 100 steps. And the person that did this and I'm going to delete a lot of these notes here. The person that created this scale, was a man named Anders Celsius. So, let's get rid of that. I don't know why that's coming over to the side here. Anders Celsius, Anders Celsius. So Celsius is the one who created the centigrade scale. So saying C is centigrade or C is Celsius, either one is correct. You'll hear me use both terms. They mean the exact same. Oddly enough, though, for some bizarre reason, Anders Celsius said, I'll call the bottom 100, and I'll call the top 0. And later on, somebody said, well, that doesn't make a lot of sense. Let's call the top 100 and the bottom 0. So, but we still name it after Celsius because he created the whole scale. So Celsius and centigrade are exactly the same scale, and the temperatures are 0 and 100 degrees for the freezing and boiling point of water. But in any case, you have this container at a certain temperature, and one container has twice as much water as the other. So while they have exactly the same temperature, the one on the right contains twice as much heat energy stored in it because there's twice as much water there. So when we're measuring temperature, we use thermometers, and we think of temperature as a measure of how hot and cold things are, but it's really a measure of heat energy. It's even more correctly defined as a measure of how much thermal energy, kinetic energy, is in the molecules you're measuring, or even how fast they're going. So we have temperature conversion scales because so many people use different scales. We've already talked about Fahrenheit and centigrade. There's another scale you need to be familiar with called the Kelvin scale. I've already mentioned that earlier. And we don't change the sig figs when you convert. I know it's very confusing, but for now we'll just keep it at this simplified definition. If you have 3 sig figs to start, you'll end with 3 sig figs. There are more complicated rules, but for now let's keep it at that. And maybe it's better to say the number of decimal places rather than sig figs. I will always give you how many decimal places or sig figs I want for temperature conversions because these are a bit confusing. So converting Fahrenheit to centigrade, if you want to convert centigrade to Fahrenheit, you use the first of these formulas. You'll multiply the centigrade value times 1.8, and then you'll add 32 degrees to get the Fahrenheit. And if you want to go backwards, well, you do the opposite. Instead of multiplying by 1.8 and then adding 32, well, first you do the opposite. You subtract 32, and then you divide by 1.8. So you have these two formulas, and these are in your conversion factor table at the very bottom under temperature. Now we have this other scale called the Kelvin scale. And the Kelvin scale is interesting because the Kelvin scale is very similar to the centigrade scale. So the Kelvin scale, if we have the exact same temperature, and one thermometer is in centigrade and one is in Kelvin, sorry, it's supposed to be degrees, this one might read 0 degrees centigrade, but 0 degrees centigrade is not the coldest temperature possible. As it turns out, the coldest temperature possible is way down here. It's minus 273.15 degrees centigrade. Well, there's another scale that was named after a very famous scientist called Lord Kelvin, and this scale says, okay, let's start at 0 instead. Let's not start at minus 273.15. That's kind of an awkward number. Let's start at 0 so that all our temperatures are always positive numbers. And this makes calculations much easier. So when you're doing special calculations, when you're doing gas law calculations and other calculations, you almost always have to use Kelvin. There's actually one exception that we'll talk about in the very next module that you can use Celsius for or centigrade for, but in general you have to use Kelvin. So Kelvin, since we start at 0, that means what used to be 0 degrees centigrade is now positive 273.15. So the size of a Kelvin degree is exactly the same as the size of a Celsius degree. It's just that Kelvin starts at 0. So the conversion for Kelvin for centigrade to Kelvin, you just add 273.15 to whatever your centigrade value was, and you'll get your Kelvin. And going backwards, you just subtract it out. So let's use this in some calculations. So I'll allow you to practice this. This is 350 degrees Fahrenheit, so this is a typical cooking temperature. What would it be in centigrade? Well, you're going from Fahrenheit to centigrade, so you need to use this formula here. You're starting with Fahrenheit and you're getting centigrade. So you're going to use that. You're going to subtract 32, you're going to divide by 1.8, and you'll get your answer. If you look at the next problem, minus 20 degrees centigrade, now you're starting with centigrade and you're going to Fahrenheit. So you're going to first multiply it by 1.8, so you'll have a very negative number still, and then you're going to add positive 32 to that, and you'll get your number. So let's look at these values. You'll get 177 C, 177 degrees centigrade or degrees Celsius. So 350 degrees Fahrenheit, typical cooking temperature, is about 180 degrees centigrade. Minus 20 degrees C, that's a pretty cold temperature. That's actually freezer temperature in laboratories. That's minus 4 degrees Fahrenheit, and you see this quite often as a lab temperature for certain experiments or certain storage conditions. Minus 20 C is very common. So I'm going to leave these up to you. You've got the 23 degrees C. You merely have to add 273.15 to that and round it, since you only had 2 sig figs. You only had, I should say, not 2 sig figs, but you only had to the nearest degree here. So you want it to the nearest degree here. So we're keeping the number of degrees, number of decimal places the same. So we went to the nearest 1, we're going to go to the nearest 1. So sig figs in this case doesn't really mean sig figs, it means decimal places. So if you had it to the nearest 1 degree, you still want it to the nearest 1 degree Kelvin. And I'll leave the rest of these up to you, but I'm going to stop for just a second here. You pause it if you'd like to do the other two. And now I'm going to show you the other answers. So 600 degrees Kelvin, you merely subtract out the 273.15. And 98.6, this is the average body temperature in Fahrenheit. You'll notice it comes out to a nice round number of 37.0 degrees centigrade. So if you're ever in a country outside of the U.S. and they're using a different temperature scale, you'll know what body temperature is. It's 37. And with this, we'll stop here and continue on with calorimeters and more calorimetry.